Actually, you're looking at this one up here. All right, so ionization constant, if it's acetic acid, you assume that constant is Ka. All right, and so if you want the Kb, we have this simple expression Ka times Kb equals the Kw. And Kw, unless otherwise indicated, we take that to equal 1 times 10 to the minus 14th. So plug that in, plug in the Ka that's given, divide, and you should get 5.9 times 10 to the minus 10th. So that was question 3, which I think is what you were alluding to there with your first inquiry. Question 6, how to find the Ka using the pH. So if we are given 0.25 molar of an unknown acid, doesn't really matter what the acid is, but it's got a pH of 2.5, what's the Ka? So we know that for Ka, we either need to know the Kb or we need to know the hydrogen ion concentration. And given that we are given the concentration of the weak acid, it's probably going to make sense for us to use the Ka expression, which uses both that concentration and the hydrogen ion concentration. So with the given info of pH, again there we could either go to POH or we could go to the hydrogen ion concentration. So this is the route we're going to go. So to find the hydrogen ion concentration, you have to undo that pH calculation. So you're going to take 10 to the negative pH value, which is going to give you 3.2 times 10 to the minus 3rd molar. All right, and again, just with a generic equation, all right, we assume that whenever an acid's going to ionize, it's only going to lose that first proton. So it's just treated as if it's monoprotic. And setting up your Ka expression for that generic equation, it's a 1-to-1 ratio. So if this is your hydrogen ion concentration, we also assume that it's the anion concentration as well. 0.25 molar is your weak acid concentration. So plug and chug, and you should come up with 4.0 times 10 to the minus 5th for that Ka value. All right, so this was the next question you were asking about, finding the pH from the Kb and the concentration. And what you need to note is that NH3 is a weak base. So if we are going to talk about its equilibrium, you're going to have ammonia in equilibrium with the ammonium ion plus the hydroxide ion. Again, water's absent because water's concentration doesn't change at all. So the Kb expression is going to be concentration of ammonium ion times concentration of hydroxide ion divided by concentration of the weak base. And we're going to let X equal the hydroxide ion concentration. Again, when you're approaching these problems, depending on what you're asked, whatever you're asked for, think, what are the ways that I can get to that value? And then you also want to ask, from what I'm given, where can I get given that information? So like with Kb, I can go to Ka, or I can get to the hydroxide ion concentration. All right. With pH, I can get there from POH, or I can get there if I know the hydrogen ion concentration. But given the fact that I know the concentration of the weak base, that's usually when you're looking at the equilibrium expression. Okay? So we're going to take that pH and we are going to take the Kb, excuse me, all right? And we are going to use that along with the concentration of the weak base and figure out what those X values should be, okay? So when we substitute that in, we're going to get 1.8 times 10 to the minus 5th. All right, rearranging times concentration of the ammonia, which is 0.5 molar. And that's going to be equal to X times X, or X squared. All right, and so if we take and do our plug and chug here, and so we're going to have 0.00018, and I'm going to multiply that by 0.5. That's going to give me 9 times 10 to the minus 6th, and then I need to take the square root of that, so that's going to give me 0.003. Okay, or 3 times 10 to the minus 3rd molar. All right, so if that's 3 times 10 to the minus 3 molar, and that's hydroxide ion concentration, Okay. Now I've got some options here. All right. If I know the hydroxide ion concentration, I can figure out the pOH. And if I know the pOH, then it's a matter of subtracting that from 14. So let's go that route. To find pOH, we're going to take the negative log, all right, of 0.003. And in doing that, so we're going to take negative log 0.003. All right, and that's going to give us 2.5. But again, that's the pOH. So to get the pH, we're going to take 14 minus the pOH value. So we bring that up and plug it in. And so pH is going to come out to be, all right, 11.5. All right. Now the last question you asked about is finding Kb from pH. So once again, all right, if we know the pH, from pH we can go to either pOH or the hydrogen ion concentration. All right, if we and we have the concentration of the weak base. So again, that kind of suggests let's work with the equilibrium expression. So pOH is going to be equal to 14 minus the given pH, so that's going to give us 4.3 for the pOH. Finding the hydroxide ion concentration, we take 10 to the negative pOH, so that's going to give us 5.0 times 10 to the minus fifth power. And now that we have that, if we assume that our weak base just has the generic formula MOH, we're going to get the metal for the cation and then hydroxide ion, so your Kb expression would be as we see here, and 1-to-1 ratio. So we're going to assume that we have 5.0 times 10 to the minus fifth for the concentration of both the metal ion and the hydroxide ion, divided by the weak base concentration, 0.045, and that should give us 5.6 times 10 to the minus eighth. So in these calculations involving pH, pOH, Ka, Kb, hydrogen ion concentration, and hydroxide ion concentration, it's all very circular. That if you have one or even two pieces of information, you can literally calculate everything else using those basic ideas of Ka times Kb equals Kw, pH plus pOH equals 14, your Ka expressions, your Kb expressions, and using all of those together in a stepwise fashion, you can figure out most any value that you need. All right, hope this helps.